Hello and welcome back to C Puzzles. In this video we will try to wrap up operators for bitwise operators. We will try to finish up the last three puzzles of this section, which are operators 4.8, 4.9, and 4.10. For those that are new, we do puzzles out of the C puzzle book by Alan R. Feuer. There should be a link in the description to a copy of the book if you want to go ahead and check that out for yourselves. But nonetheless, here again we have the snippet of code along with the three puzzles that we are trying to solve. We got x left shifted by 3 to the left, and then we go ahead and call the print macro. We got y left shifted by 3. Then again we'll call the print macro, and last but not least we have y right shifted by 3, and then we'll call on the print macro. Feel free to go ahead and pause the video and try to solve these exercises yourself. Then we'll come back to the solution, but for now let's go ahead and jump to run this actual code. Alright, welcome back. Once again, here we have Visual Studio Code up and running, and again we've added these new lines of code, lines 19 through 21, which don't have any comments here, but these are going to be operators 4.8 and then 4.9 and 4.10 respectively. So just mark it out here, making it clear. Alright, so now that we go ahead and try to save this and compile our code, let's go see what the output of these last three statements are. Here again, we're using GCC as our compiler, and then running the executable. We see here that the results of the puzzles, we have for 4.8, x is equal to 8, 4.9, y is equal to -8, and last but not least, y is equal to -1 for 4.10. And let's go ahead and jump to the solution and explain how we got these three results. Alright, welcome back, and before we actually jump into the solution, let's go ahead and talk a little bit about these compound bitwise shift, just so we have a little bit of example of before we actually jump into the solution. So again, we saw in the puzzles that we have some sort of form of x right shifted by n bits, this statement right here, or x left shifted by n bits over here. X left shifted by n bits, or this expression here, is equivalent to saying x is equal to x less than n, meaning that we take the value of x, we left shift it by n bits, and the result of this shift gets assigned back to the value of x. Equivalently, if we were to take x and right shift it by n bits, same thing as saying that we're going to right shift x by n bits and then assign that resultant shifting back to the variable x. The common colloquial term is that we'll left shift all bits to the left by n bits, or right shift all bits to the right by n bits, or equivalently you hear shift by n bits either to the right or to the left. An example I have here, we have the value of x being a value of 1 in its binary representation form. If we were to go ahead and left shift x by 0 bits, we can see that there is no change in the resultant. This is because left shifting or right shifting by 0 bits does not change the value itself, since the bits are not moving, or they're moving 0 positions, so they're remaining intact. If we were to go ahead now, take again value of x and left shift x by 1, we can see here through my color-coded scheme here of the individual bits that the value of 1, which was originally in the bit 0 spot, has now shifted to the B1 spot. You can see here originally in the B1 spot we had the blue square. Value of 0 is now left shifted into the B2, and in the B2, which was the teal, has now been left shifted to the B3, and then this pattern continues on and so forth. So we can see that all the bits have left shifted to the left by 1 position. In the B0 spot we have inserted a 0, as this is usually the case when we do these kind of shifts, although there is some caveats here, but nonetheless this is known as a logical shift, and logical shifts will insert zeros into the remaining spots as you continue left shifting by n number of places. The resulting value of x left shift by 1 we can see here is the value of 2. Here is its binary representation form. And we can see that by left shifting x by a value of 1, we've essentially multiplied or doubled the value from 1 to 2. And this is again the case when you keep left shifting. If we were to left shift x one more spot, that would equivalent to multiplying 2 by 2, so we get a value of 4, and so forth. Going back into operators 4.8, again we have integers x, y, and z. Their respective values at initialization were 1, -1, and 0. These have not changed since operators 4.7. And again, we are looking at or trying to solve the expression of x left shifted by 3 bit positions, followed by the call to the print macro. In here we have in the gray box here, we have the proper syntax following the ISO 9899 standard. We can see that the proper terminology on the left hand side is the shift expression. On the right hand operand side we have the additive expression. So looking back at our code, x will be essentially our shift expression, where 3 would be the additive expression. Again, going to operators 4.8, we have value of x, which is a value of 1. And here if we left shift x by 3 to left, we can see that each color-coded square box has now shifted to left by 3 spots. You can see that the 1 in the B0 has now been moved to the B3 spots in the resultant value. And we can see that, as I mentioned before, zeros have been inserted on the right-hand side of the B0, B1, and B2 bit locations. And the result of this x left shifted by 3 is now 8, this being the binary form or representation of the decimal value of 8. And again, just noting here, passing in the value of x, and then converting that x into a string form, printing the value of x in decimal value, we can see that x equals 8 is what we saw when we ran operators 4.8 in the code. For operators 4.9, the puzzle under question is now we are left shifting y by 3 bits. So really similar to what we did in operators 4.8, except now we're left shifting y instead of x by 3 bits. Recall again that y has been initialized to a value of -1, and showing -1 in its binary representation form for a 2's complement machine here, we can see we have a value of all ones in all bit positions for a value of -1. Going to go ahead and shift all bits to the left by 3 spots. We can see that we're going to also insert zeros in the vacant bit locations. We can see here that bit 0, bit 1, and bit 2 all have zeros, as is expected when we go ahead and left shift the value of y to the left. And we can see here at the upper bits, we still have values of 1, as we're going to go ahead and keep the sign bits, which I'll explain a little bit shortly. But nonetheless, left shifting y by 3 bits to the left gives us a result value of -8. Once again, passing in the value of y into the print macro and converting that y into a string and printing out the respective value of y in decimal format, we can see again that y is equal to -8 as we saw from running our code. Alright, for operators 4.10, now we have the puzzle where we're shifting y to the right by 3 bits. So similar to 4.9, except now we're right shifting instead of left shifting. Again, recalling from operators 4.9, the resulting value was y was a value of -8. If we were to go ahead now and shift all bits to the right by 3 spots, we'll go ahead and insert the sign bit on the leftmost bit, and therefore we can see that we move all bits to the right by 1. We essentially get back what we originally had as -1 for a y value. Again, passing in y into the print macro, we can see once again we're converting y to a string and then printing the decimal form of y, which again is -1. And we can see that y equals -1 gets printed out as expected and as we saw from running our code. If you made it all the way to the end of the video, thank you again for watching. If you like this video, please feel free to give a thumbs up or leave a comment. To watch the previous puzzle, click on the bottom left hand corner. To watch any of the previous C puzzle videos, click on the playlist that will show up in the middle. And to subscribe for any more future C puzzle programming content, click on the bottom right hand corner. And I'll catch you all in the next video.